Let's take a look at the graphs of logarithmic functions. Our objective: graph logarithmic functions and recognize their properties. We're also going to compare their graphs to their inverse functions, the exponential functions. Okay, what do we know here? We know the exponential functions, which are written f of x equals a to the x. Again, the exponent is the variable in an exponential function. And the logarithmic functions, f of x equals log base a of x, are inverse functions. They undo one another. The second thing we know, the graphs of inverse functions are symmetrical with respect to the line y equals x. And we're going to look at that at the end of this video lecture. And the third thing we know are the properties of the graph of an exponential function. The domain goes from negative infinity to infinity, the range from 0 to infinity. An exponential function has no x-intercepts, and its y-intercept is at 1. The x-axis is a horizontal asymptote. When a is greater than 1, the exponential function is increasing. When a, the base, is between 0 and 1, less than 1 but greater than 0, it is a decreasing function. The exponential function f of x equals a to the x contains the points 0, 1, 1a, and negative 1, 1 over a. And finally, these graphs are smooth and continuous with no corners or gaps. Now let's take a look at logarithmic functions. So we're going to graph these three. We're going to graph as y1 log base 2 of x, as y2 log base 5 of x, and as y3 the common log base 10 of x. Again, if we use the log key, the 10 is assumed. And let's take a look at how these functions look, their similarities. So I'm into here and I put them into the calculator. Log base 2 of x is y1, log base 5 of x is y2, and log base 10 of x is in y3. And I'm going to press graph. And so there is the base 2. There's the base 5, and there's the base 10. Okay, so it looks like they all have some similarities. Let's kind of zoom in a little bit. We can see the base 2 comes out. It looks like it's a little bit steeper, and then it comes out and it's above. They're still growing. They're all growing as they go from left to right. The base 2 is above the base 5, above the base 10. Let's zoom in and let's take a look at what's going on around the point here, 1, 0. So my window, I'm going to go from negative 1 to 2. And I don't need to go quite so high. I'll go to 5 on the y-axis. Here comes base 2. Here comes base 5. And here comes base 10. Okay, well, clearly, we know the domain, positives, and we know the range. Well, they go down from negative infinity, and they go up to infinity. We saw that in our previous video lecture. The range goes to infinity. It takes a heck of a long time to grow, but once, if you go out to infinity, it'll eventually get to infinity for the range. They all cross at the point 1, 0. That's nice to know. And if we go into the table, I'll go second table. If we look at the first one, remember it was base 2. Well, the point 2, 1 is here. If we look at the base 5, here's the one that's base 5, which was y2. 5, 1 is here. And if we look at base 10, which was the of x, the base 10, here's 10, 1. Okay, so they all have some commonalities very similar to our exponential functions. Let's do the same thing so these bases were greater than 1. Okay, a 2, a 5, and a 10. Let's look at bases that are between 0 and 1, so our proper fractions. Let's look at 1/2, 1/3, and 1/10 and see what's going on. Okay, back to this one, notice again they're all increasing. So when the base is greater than 1, all of them are increasing. Let's go back to our y equals, and let's clear these out. And now let's put in bases that are proper fractions between 0 and 1. So I'm going to go and choose my log. This base is going to be 1/2. So I'll put 1/2 in here for the base and put in for x. And let's just graph it. Oh, it's coming down from above now. It's a decreasing function. So let's get my window and let's do my, let's go a little bit higher on my y. Okay, now let's graph. There we go. Well, I get a decreasing function with a proper fraction base. I'm still going to the point 1, 0, but it's decreasing. Let's try that base of 1/5. So let's do my log with a base of 1/5, a smaller base, and we'll see, okay, same thing, it's decreasing. It's still going through the point 1, 0. It still has an asymptote of the y-axis. It has an x equals 0 asymptote. And notice it's not touching the y-axis. There are no y-intercepts. So there's one x-intercept, no y-intercepts. X equals 0 is a vertical asymptote, and they're decreasing all the time. Let's go back into here and put a base of 1/10 in. So I'll put in a 1 divided by 10 base. And I think we'll still get a decreasing. It's just decreasing a little bit. It's decreasing more slowly. So a faster decrease to a slower decrease. Still crossing, still has an intercept at 1, 0. Still has an asymptote of x equals 0, the y-axis. Still does not have a y-intercept. Let's see, and it's smooth and continuous. So we can use what we just saw to summarize similarly for the logarithmic functions. I've done that on the back. Okay, so the properties of the log function, here it is, f of x equals log base a of x. Now, a must be greater than 0, your base, you can't have a negative base. And a can't be 1. If a is 1, 1 to anything is 1, and there's really nothing interesting about that. So we want to be focused on our bases that are greater than 0, but not including 1. Well, as we knew, the domain of 0, the domain of the log function equals the range of the exponential function. So the domain is 0 to infinity. The range goes from negative infinity to infinity. It grows to infinity very, very slowly, but it does keep growing. Okay, there's an x-intercept at 1. There's no y-intercept. If you'll recall, with our exponential function, there's no x-intercept, but there's a y-intercept at 1. So those two things are reversed. Okay, in our log function, the y-axis, or x equals 0, is a vertical asymptote. We'll compare that to our exponential function, where the x-axis, y equals 0, is a horizontal asymptote. Again, kind of the opposite. Okay, we notice here with exponential that when the base is greater than 1, it's increasing. When the base is between 0 and 1, it's decreasing. This is similar. This is the same thing for the log function. When the base is greater than 1, it's an increasing function. When the base is between 0 and 1, it's a decreasing function. So, as my brother would say when he was a little kid, same. Contains the log function contains the points 1, 0, a1, or the base, comma 1, and 1 over a, comma negative 1. Some similarities there with the exponential function. Some opposites. I think the exponential function is 0, 1, 1a and negative 1, 1 over a, so they are switched because they are inverse functions. And of course, just like the exponential function, the log function is smooth and continuous with no centers or gaps. All right, let's take a look at these two functions that are inverse functions, and let's compare them. We know that because they're inverses, they should be symmetrical with respect to the line y equals x. So let's take a look and put these things together with their graphs. So I'm going to go into here, y equals. I'm going to clear these out. And let's graph the log base 2 of x. Log base 2 of x. I'm going to go to I'll go to my standard window, and we know this is what it looks like. On the same graph, let's do 2 to the x, which is the inverse function, 2 to the x. So y2 is 2 to the x, and I'll graph that. And here it comes. And you can see they're both growing. This one starts from here. It grows and grows and grows. It grows quickly at the beginning, and then its growth slows down. So the log with a base 2 greater than 1 is an increasing function. It increases quickly, and then it increases more and more slowly, but it is still increasing. Exponential function is an increasing function. It's increasing very, very slowly, and then it begins to quicken, and as it passes through the point 0, 1, it increases faster and faster and faster. Let's graph the y, let's put y3 as y equals x, and you'll see the symmetry. There's your symmetry. Growing faster, growing slowly, more and more slowly, getting symmetrical. There's symmetry right about here, the distance away, and then you can see the symmetry as we work here about that line y equals x. So again, with a base, the a being greater than 1, both functions are increasing as you move from left to right. Now let's look at bases that are between 0 and 1, bases that are proper fractions. Okay, so this is going to be, let's clear these two out. I'll leave y equals x in there. Okay, so this is going to be the log base 1/3 of x. And the second one is going to be 1/3, here I am, 1/3 to the x. So I'll put in parentheses 1/3, and I'll raise that to the x power. Again, these are inverse functions. They should be symmetrical with respect to the line y equals x. They undo one another. Graph. Well, there's the decreasing function, the log function. Here is the decreasing exponential function. And here's the line y equals x. So you can't really tell, but this, of course, is going up and up along that line. But you can see the symmetry here. They both cross wherever that point is. But they're both decreasing. The log decreases. They both decrease quickly, and then they slow down. Decrease quickly and slow down. But they're both decreasing functions. And they're symmetrical about the line y equals x. So there you have it. A look at the graphs of the log functions and their properties.